James Webb's discovery of the interstellar comet 3I/Atlas is utterly defying our understanding of physics, an astonishing cosmic anomaly that remains stubbornly in one piece, despite shedding seemingly impossible amounts of mass. These are the very latest images of 3I/Atlas, and I'm convinced this revelation represents the most shocking enigma we've encountered regarding this enigmatic object. Until now, the only logical explanation for its bizarre behavior was that it was in the process of violently fragmenting. So, let's delve deep into this cosmic mystery and unravel everything we currently understand about what's truly unfolding with 3I/Atlas. First, let's explore why the scientific community was so profoundly convinced that this object must be fragmenting, shattering into countless pieces. Then, we'll pivot to unveil the startling truth revealed by these brand new images. Earlier observations captured breathtaking images, showcasing not just one, but two magnificent tails, a primary tail and a sunward-pointing anti-tail, each stretching for millions upon millions of kilometers across the cold vacuum of space. However, when we consider typical cometary physics, gas streams from a comet's nucleus at a relatively sluggish pace, merely around 1,500 kilometers per hour. To put that in perspective, for a comet's tails to extend to such colossal lengths, millions of kilometers, at that speed, the object would have to be relentlessly spewing out gas, without pause, for a continuous span of several months. Yet, here's where the plot thickens. Images taken just a few days prior to those showing the sprawling tails depicted absolutely no tail whatsoever. This sudden, inexplicable appearance of such immense structures is just one of the many perplexing facets of this comet. Further compounding the mystery, to generate such prodigious tails, 3I/Atlas would theoretically require a surface area of approximately 1,600 square kilometers actively absorbing sunlight. Imagine a sphere a staggering 23 kilometers in diameter. That's the equivalent surface area. But when the venerable Hubble Space Telescope meticulously measured 3I/Atlas, it revealed a far more modest object, only about 5.6 kilometers across. The cold, hard math presented an impossible scenario. The comet needed to be nearly 4 times larger than its actual measured size. This profound discrepancy led us to calculate the sheer volume of material these colossal tails must be stripping away from 3I/Atlas. The resulting figures are nothing short of breathtaking. Frankly, quite unsettling. Estimations indicate that 3I/Atlas is losing an astonishing 50 billion tons of material every single month. This figure becomes even more disturbing when juxtaposed with the comet's estimated total mass, which is thought to be only around 33 billion tons. How can an object possibly lose more mass than it actually possesses? It defied fundamental principles. Now, while seemingly unprecedented, we have, in fact, witnessed a similar phenomenon before. Consider the dramatic fate of Comet Shoemaker-Levy 9, which spectacularly broke apart in 1992. The total amount of material it eventually released far exceeded what astronomers initially believed the original comet weighed. However, this paradox made perfect sense once we understood that it had shattered into 21 distinct fragments. These numerous pieces, acting like a multitude of smaller comets, presented a vastly increased total surface area. This amplified exposure allowed the sun's relentless heat to convert far more ice directly into gas, fueling an explosion of visible jets and creating more extensive, brighter tails. Therefore, the only conceivable, logical explanation for the 7 distinct jets observed, coupled with the massive, multi-million-kilometer tails depicted in the images of 3I/Atlas, was that the comet must have fragmented into countless smaller pieces. After all, by all known physical laws, a single, solid object simply cannot shed more mass than its entire being comprises. So, let's turn our attention to what the new images unequivocally reveal, a truly astonishing twist in this cosmic tale. 2 esteemed astronomers, David Jewett and Jane Liu, meticulously aimed a powerful telescope situated in the Canary Islands directly at 3I/Atlas. When they eventually published their groundbreaking findings, they opted for a remarkably concise, yet profoundly impactful, title: 3I/Atlas, Still Single. Let that sink in. Not broken into a constellation of pieces, not actively fragmenting, not scattering a vast debris field across the void. It remains stubbornly, miraculously intact. But what imbues these particular images with such immense importance is not merely the superficial observation. They didn't just glance and declare, "Yep, it's still together." No, their rigorous investigation involved measuring and analyzing every conceivable detail with painstaking precision and scientific exactitude. The newly captured images precisely pinpoint 3I/Atlas approximately 1.5 astronomical units from the Sun, a colossal distance of about 214 million kilometers. It's also a little over 2 astronomical units from Earth, placing it roughly 320 million kilometers away. Crucially, their observations encompassed a vast region around the comet, stretching nearly 500,000 kilometers wide. This immense observational field was meticulously scrutinized, specifically designed to uncover even the faintest whisper of a breakup, any telltale sign of fragmentation. What their exhaustive search yielded was a singular, brilliant nucleus, the solid, icy heart of the comet. Encircling this nucleus was an active, ethereal cloud of glowing gas and dust, known as the Comet, which itself displayed a surprisingly complex and structured morphology. They indeed observed two distinct tails, extending in diametrically opposite directions, just as seen in the earlier images that had initially baffled us. One tail was pointing almost directly towards the Sun, its angle measured at approximately 106 degrees. With the Sun located at about 115 degrees from their perspective, this meant the tail was pointing sunward with a mere 9 degrees deviation, a phenomenon known as an anti-tail. While rare and fascinating, an anti-tail is not entirely unprecedented. The other tail, behaving more conventionally, was pointing away from the Sun at about 301 degrees. To definitively ascertain the presence or absence of fragments, JWST and Liu employed an arsenal of sophisticated image processing techniques. They dramatically stretched the brightness of the images, creating subtle gradations. They constructed intricate contour maps to highlight variations in density. They utilized false color imaging to accentuate minute differences. They even meticulously examined the image in concentric rings, moving outward from the comet's brilliant center, as if peeling back the layers of an onion. Every single technique they deployed was meticulously crafted and executed with one overriding goal: to detect even the smallest, most elusive fragments, should they exist. Their report explicitly stated, in no uncertain terms, that the entire imaged region showed no hint whatsoever of fragmentation. Consider the implications if 3I/Atlas had shattered into 16 distinct pieces, as the earlier, seemingly irrefutable math had so emphatically suggested. Those pieces would inevitably be dispersing, spreading out across that vast observational field. They would be undeniably visible. They would leave discernible trails, ghosting across the images. Yet, the pictures showed absolutely none of that. So, we're not merely relying on a subjective impression that the object appears to be intact. We are witnessing the result of a meticulously planned and executed scientific investigation, where experienced astronomers rigorously examined a colossal region around 3I/Atlas using multiple, independent analysis methods, and found zero empirical evidence of any breakup or fragmentation whatsoever. And let us not forget the incredible journey this object has just endured. This cosmic wanderer recently navigated the most brutal, intense phase of its entire passage through our solar system, its closest approach to the Sun. It was subjected to extreme, searing temperatures, enduring immense thermal stress that, by all scientific expectations, should have caused it to crack and splinter apart. The sheer, explosive pressure generated by all that gas violently shooting out from its surface should have, by rights, blown it into a myriad of pieces. Yet, weeks later, against all odds, it remains a single, stubbornly solid object, actively producing those enormous jets in multiple, perplexing directions. Therefore, if this object is indeed a natural phenomenon, and I strongly believe it is, then the scientific community faces a profound, urgent challenge. They must explain how this astonishing resilience, this blatant death, ions of established physics, is even remotely possible. Based on current data, here are the leading theories I have right now. We understand that 3I/Atlas is likely billions of years older than our entire solar system itself, perhaps a venerable 7 billion years old, or even a staggering 10 billion years old. For all those countless eons, this comet has been traversing the frigid, desolate expanse of deep interstellar space, relentlessly bombarded by cosmic rays. These are immensely high-energy particles, stellar shrapnel, that slam into objects and fundamentally alter their atomic structure and chemical composition. Picture it as a slow, inexorable form of radiation cooking the surface of the comet over an unimaginable span of billions of years, gradually transforming its very fabric. The James Webb Space Telescope, with its unparalleled observational capabilities, has unearthed something truly intriguing that lends significant support to this captivating hypothesis. 3I/Atlas exhibits a significantly higher proportion of carbon dioxide compared to water ice than what is typically observed in normal comets, an astounding 8 times the usual ratio. This curious chemical signature could be a direct consequence of those relentless cosmic rays, tirelessly converting carbon monoxide present on the comet's ancient surface into carbon dioxide over those billions of years. This long-term cosmic ray bombardment might also have forged a truly unique and robust. Imagine a crusty layer enveloping the surface, not unlike a durable rind on an ancient fruit, but composed of supercooled volatiles and dust. This enigmatic outer shell might just be forcing the underlying ice to sublimate in utterly bizarre, unprecedented ways. Picture, if you will, a labyrinth of intricate channels or hidden pockets forming beneath this crust. These internal conduits, unseen from our vantage point, could dramatically amplify the comet's effective surface area, allowing it to vent far more material than its external dimensions would ever suggest. Could this hidden architecture be the key? Alternatively, perhaps our very foundational calculations for the required surface area are flawed. Is it conceivable that sublimation, under specific, as yet undetermined conditions, can occur at a far more accelerated pace than our current models predict? Furthermore, what if the magnificent jets we observe are not actually carrying the prodigious mass that our sophisticated calculations imply? The staggering figure of 50 billion tons of material expelled per month was derived through a complex process. We scrutinized the sheer size and luminous brilliance of the comet's tails, then meticulously worked backward, an intricate inverse problem, to deduce the immense quantity of material necessary to produce such a spectacular display. But here's a thought-provoking counterargument. What if these dazzling tails are simply extraordinarily efficient at scattering sunlight? They might be akin to a thin, expansive cloud that appears monumental and dense due to its optical properties, rather than its actual mass. In essence, they could be significantly less massive than their radiant appearance leads us to believe, creating an optical illusion on a cosmic scale. If, hypothetically, the actual mass loss plummeted to a mere 5 billion tons per month, a tenfold reduction from our initial estimates, the numbers would suddenly align with our expectations much more harmoniously. While even 5 billion tons remains an extreme, mind-boggling amount, it catapults the phenomenon from the realm of near impossibility to something at least plausible for an object of this particular size and composition. It brings the observable activity into a more consistent narrative with the comet's physical dimensions. However, a significant wrinkle in this revised theory emerges. For decades, scientists have honed and applied this precise methodology for calculating cometary mass loss, and demonstrably, it works. It has been validated against countless other comets, proving its reliability time and again. So, if this established and rigorously tested method is suddenly found wanting or wrong, specifically for 3I/Atlas, then we face a profound scientific imperative. We absolutely must unravel the mystery of why. What unique characteristics or circumstances of 3I/Atlas could be rendering our trusted equations obsolete, forcing us to rethink fundamental aspects of cometary physics. If you've journeyed with us through this deep dive into the cosmic enigma of 3I/Atlas and found this exploration compelling, consider dropping a like and subscribing for more intriguing updates on the universe's most perplexing phenomena.